Welcome. I'm going to be going over your homework step by step. All right. So John takes a running leap and jumps horizontally off of a cliff at second dam. Please be careful if you ever do this. All right. So X, Y. It is critical to keep your data separate in an XY chart. And the reason is that if you mix X and Y numbers in the same formula, it's hard for me to even find you a point. It's basically a bloodbath, okay? All right, maybe a little picture would help. All right, so we've got a cliff, we got some water, we got somebody leaving horizontally off of the cliff, and they're going to come down like this. All right, the first thing we want to know is what that height is, and that would be dy. Okay, so we also know that he's traveling at an initial velocity of 10 meters per second. Okay, all right, and it's the time it takes is 1.67 seconds to reach the water. All right, where do we put this in our chart? Well, time is the same on the X and Y. It's the great uniter, which is why in many problems it's what you find first, right? There's no such thing as time in the X or time in the Y. They're the same thing. So that's 1.67 seconds. And since he's only going down, we don't have to worry about time up and time down or anything like that. All right. Now, he's moving at 10 meters per second initially, so that's the Vx. But if you remember from your reading with projectiles or some of the early videos, the X velocity never changes. So the average is the same as the velocity at any moment, and it means we can use that really easy formula. So it's the X velocity that's 10 meters per second. Okay, and on the X side, we're always only going to use one formula because that's horizontal constant motion, and that's Vx equals d over t. That's the only formula we're going to use on the X side. Later we'll use a component formula, but that's it. All right. Now, it seems like we have too little information, but we actually know quite a bit about the Y as well. We know that since he's near the Earth, the acceleration due to gravity is 9.81 meters per second squared. I'm going to say down is the negative direction. So I'm going to make that a negative 9.8. So the acceleration is negative 9.81 meters per second squared because I'm saying down is negative and gravity pulls down. All right, and then there's one other hidden piece of information, and that is the initial velocity at the top is 0. This is a critical piece of hidden information. And basically, these both are always true for all projectile problems, with the exception of something being shot down, like with initial velocity down. And that's beyond the scope of this course because guess what? You need a quadratic equation to solve it, and we don't do that as a regular rule, at least for regular credit. Okay, so this is all we know about this problem. Now we want to know how high was the cliff. That is a y question, dy. All right, so this is what we're looking for. So now we need to pick a formula from our reference tables that has all of these things and nothing else. Okay, so we needed to have all of these and nothing else. And that formula is this one right here. Okay. So the formula I'm going to use is d equals VIT plus 1/2 AT squared. Now, you can either be super careful about subscripts and make sure you put little y's everywhere. It's dy, it's vi, you don't have to do it near t. You could put an ay here. I don't usually because the only acceleration's in the y direction. The acceleration on the x side is 0. Okay. So I usually don't bother to put the y there because if there is an acceleration, I'm assuming it's the y side. All right. Now we can sub in and substitute. Oh, we could also, since 0 times anything is 0, we can get rid of this whole term. All right, so that drops out. And so we just plug and chug at this point. So it's dy equals 1/2 times negative 9.81 meters per second squared times 1.67 seconds. Don't forget to square it. Okay? If you do all the math on that, you will find that he has a dy of 13.7 meters. I have no idea how high second dam actually is. All right, now horizontal range, that is dx. Range means the horizontal distance. All right, it's a vocab word that you need to learn. All right, so what we're looking for is here is dx. That goes over here. And again, the only formula we ever use on the x side, since the x velocity is constant, is this easy guy. And we're going to go ahead and do that. So 10 meters per second So Vx equals dx over t, little bar there. 10 meters per second equals dx, which is what we're looking for, all over time, which is 1.67 seconds. All right. What we're going to do then is multiply both sides by 1.67 and cancel that out. So I get 1.67 over here and 1.67 over here. These cancel. And I get that dx is equal to 16.7 meters. All right, done. Next, what is this vertical velocity just before hitting the water? All right, so now we have a new question. All right, I wish I had a new color, but my children have stolen all of my erasable pens. So we're just going to have to be all the same color. Yeah, because I got nothing. I don't know why I'm looking now. I looked before I even started making this video, and I didn't find any. All right, so what is this vertical? So what we want to know is the VFY, okay? Again, this is on this side. Now, we have a choice of formulas because we now know what the dy is, and that's 13.7. So we know this is true now. And that's technically a negative 13.7 since he fell that amount. All right, so we have a choice of formulas. But I'm going to probably use the easiest one, which is that VF equals VI plus AT. Let's quick look at our formula sheet. All right, so I'm going to use this one because it doesn't have any squares in it. But you could also use this one here, VF squared equals VI squared plus 2AD, and use that as well. But if I can do easier math, I will do it. All right, the VI, again, is 0, so I can get rid of this whole term. So the VF equals the A, which is negative 9.81. Again, because negatives are down direction, and the time is 1.67 seconds. And if I do the math there, I get that the VF is a negative 16.4 meters per second. You should get that number as well if you use the other formula, but realize you'll have to put the negative in yourself, because when you take the square root of a number, you're supposed to put in a plus or minus and then choose the right answer, and since this is going down at the end, it's negative. All right. What is its horizontal velocity before hitting the water? Well, that never changes. Okay, in free fall. So it's going to also still be what it was at the beginning, which is 10 meters per second. All right, and now vectors are rearing their ugly head again. All right, so now we got to take those final answers and find his final velocity. So what's actually happening is he comes down in his parabolic trajectory. The instant before he hits the water, he has a x velocity of 10 and a y velocity of negative 16.4. We could sketch in the resultant here, which is that. And if we want to figure out how big that is, we need to use Pythagorean theorem. All right. So you could say x squared plus y squared equals the resultant squared. I don't know, some kind of variation of that formula. So x is the 10 meters per second. Don't forget to square it. Plus the y is negative 16.4. Be a little careful about actually realize that when you square that negative number, it's going to go away. So maybe don't even put it in your calculator and risk messing up your order of operations. All right, let's do this real quick. So 16.4 squared is, and then I'm going to add that to 100, which I messed it up, 16.4, square it, and I get that r squared is 368.96. Then I'm going to take the square root of both sides, and I get that that is 19.2. So the velocity, the diagonal velocity, is 19.2 meters per second. And that's this guy right there. Okay? So we had a Vx, we had a Vy, and now those turn into that. Now, if you remember, you also need this angle here, all right, or technically this angle here. So to get that, I did inverse tangent of y over x equals theta. This is not on your reference tables, but we derived it many times. And remember, the y floats up because it's lighter, because it doesn't have this extra leg like the x does. All right, so if I put in my calculator, and I remember to be in degrees, not radians, and I'm just going to put in 16.4 as my y. I'm not going to put in the negatives, and the x was 10. The reason I'm not putting negatives in because it gets you in the wrong quadrant half the time. All right, so, all right. And I need to take the second tan of that. And I get 59 degrees. All right, now you can either subtract that from 360 or you can just say it's a negative 59 degrees. And I'm okay with that here too. Okay. All right, now, last problem. All right. And this is a more typical problem. All right, so he's going at a horizontal jump on Trojan, right? So he's coming down, woo, and then there's a horizontal jump. This is him snowboarding off of it, and then he's going to go boop, beep, 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 and then land like that. All right? So we know that this distance is 7 meters, and we know his initial velocity is 20 meters per second. So again, I'm going to make the XY chart. This is critical. People who don't make a chart, if you're not absolutely super careful with your X and Y subscripts, you end up mixing X and Y, and I can't even find you a point. Don't do it. All right, Vx, that's the one that doesn't change, is 20 meters per second. And we know that the horizontal distance, dx, is 7 meters. And now we want to know the time of flight. And if you, even if they don't ask you time first, usually you need to find time first in order to find the answer. But we're breaking it down for you right now. So we're looking for time, and that's the same on both sides. Okay. Now we have enough information to find that, because the only formula we ever use on the x side is this one. So I'm just going to plug in dx equals dx over t. All right, so 20 meters per second equals 7 meters all over time. Some people goof up their algebra when the time's on the bottom bottom of the thing. So if you do that, like cross multiply, that's what I mean by this little sign. So boop. I'm going to go 1 times 7, I'm dropping units, equals 20t. Divide both sides by 20. And I get that t equals 7 over 20, which is 0.35 seconds. And that's now true for both sides. Now, we want to know what vertical distance, that's dy. That's over here. Now, again, might be intimidating. Doesn't look like we have enough information. But the same information from the first problem is still true. It's still near the Earth's surface, so acceleration due to gravity is negative 9.8. I'm going to use down as negative unless there's a good reason not to. And then also, since he's jumping horizontally, his VI is 0 at the top. And again, these are for the Y side. You don't have to be super careful with subscripts if you're going to use the chart. But all right, we're going to use that same formula we did before. This one, d equals VIT plus 1/2 AT squared. So d equals VIT plus 1/2 AT squared. And again, good idea to put little subscripts in if you're not being super careful with the chart. All right, since he's not going any vertical distance at the or velocity at the beginning, that whole term drops out. And I get that dy equals 1/2 times negative 9.81 times the time, which was 0.35 seconds. Don't forget to square it. And when you do the math on that, you get that dy is negative 0.6 meters. He falls 0.6 meters. Okay? And that's that. Ooh, made it under 15 minutes.